Hello. So let's look at the design of a column in simple construction. As we saw in the lecture, in simple construction, there is no restriction to movement at the joints. So we can actually have some rotation in there, and that accounts for computation of some nominal moments, even though you're saying you don't have restriction to movement, but it allows for you to factor in some bits of what moments. So we'll see how we get that done. In this example, we have the column under compressive force F, and in one direction we have a beam that is connected, and the reaction from the beam is giving us 200 kilonewton, and in the other direction, that is towards the screen, we have a force of 75 kilonewtons. So we'll have to find a way of finding the compressive load due to these forces, and also the bending that they contribute to the loading of the column. And then we have the end conditions. This side is pin with the description up there, and this side is what fixed. So these two end conditions would help us get the effective length coefficient. And of course our column is 7 meters long. The grade of steel is S275. So that said, let's see how we get the computation done. Of course, we know that in column design we do try and error. So we just have to pick a section from the section table with its properties. Then we try to check its resistance to the compressive load applied. So in this example, this column was selected with the modulus of elasticity given. And also we are told the section is what's plastic. That is, the section classification is already done. So if it's not done, you would have to determine that. So from here we move to the loading process. So we have to get the axial load on the columns. We have one from the column A and the other from column B with their specific loads. Then a 5 kilonewton is picked as the self weight of the column. So when we do our computation, we add this, we have 280 kilonewton as the axial force. Now, because of the connection, here we have a connection in a simple construction, and here it is assumed that you have web plates here, that is your beam to the column connection, web plates, or any of the three types of connections that we looked at. And the theory behind this is that once you have these types of connection, you're going to have some eccentricity, that is from the reaction of your beams. So your beam applied this way, once it's connected here, so you give an offset of 100 millimeters from the face of the column. So what it means is that for this column you have 100 millimeters from the face, and then you're going to take your diameter of your column, divide it by 2 and add it to the 100, and that will be your eccentricity in this direction. So for column B, for beam B, also from the face of your column, so here you are talking about the web, so you take 100 millimeters from here offset plus what, so here you're talking about the web, so we pick the web, we divide by 2 and add it to the 100 millimeters to give us the eccentricity. So once we have that, we have the respective eccentricities on the x direction, and that's on the y direction. So now we go on to calculate the moments due to these eccentricities and the forces. So in the x direction, we have the reaction A times the eccentricity that we've calculated. So that we get our moment, and we'll do same for the beam B. We get our moments. So once we have this, our next step would be to compute the effective length. So as I said, depending on the end conditions, we get the moment coefficient. So we open the code. So when we open the code, table 22 of the code, given the end conditions that were given, effectively held in position at both ends and restraining direction at one end for non-sway mode. So going to get our coefficient, that's what, 0.85. So we move back to our computation. So we have our effective length with the length of column given